Okay, welcome back to the show, everyone. This is part of our AI paper podcast series where we really get into the weeds of important research.
And today we're tackling one called 1.58-bit FLUX.
Right. Now, we see these incredible text-to-image models all the time, just stunning stuff. But, well, there's always that catch, isn't there?
There is. They are huge. We're talking billions and billions of parameters, and that means, massive file sizes, sure, but also just enormous memory requirements when you actually try to run them.
Absolutely. It's a real bottleneck, makes it super challenging, sometimes just impossible to deploy them on, say, normal consumer hardware, or forget about mobile phones.
Exactly. And that's the heart of what this paper is trying to fix. How do you take a top-tier model and make it way, way more efficient? Their answer involves extreme low-bit quantization.
No, we usually cover the absolute latest papers, but we're actually circling back to this one from late last year. Some recent discussions we had, especially around FLUX.1 context, kind of prompted this revisit. It gives some really important background.
It really does. It sets the stage nicely.
So yeah, our mission today, let's unpack 1.58-bit FLUX. We want to figure out how they did it, how they got these efficiency gains, look at the results, performance, quality, the whole deal, and think about what it means for actually using these models more widely.
Sounds good. Let's maybe start with a quick, 1-minute rundown, the absolute key point.
Perfect for a quick summary. Okay, so the big headline. This paper introduces 1.58-bit FLUX, and they claim it's the first time anyone successfully quantized the state-of-the-art FLUX.1 dev T2I model this aggressively.
And the core technique. They took 99.5%, almost all, of the Vision Transformer's 11.9 billion parameters and squashed them down to just three values, reg of 1, 0, 1 plus 1. That's the 1.58-bit part. It's like a shorthand for that Mangus 1, 0 plus 1 scheme.
The results are pretty dramatic. A reported 7.7 times reduction in model storage size. So the file is way smaller. And maybe more importantly for actually running it, a 5.1 times reduction in the memory needed during inference. That's across different GPUs too, like V100s, A100s, but also L20s and A10s, which you might actually use for deployment. Figure 2 in the paper shows this.
Yeah, and getting that memory reduction wasn't automatic. They had to build a custom kernel, basically, special software optimized just for doing math with these 910 plus 1 values really fast on the GPU. Standard stuff isn't set up for it.
Right. And despite basically turning 99.5% of the model's brain into just 3 settings, they report that the image generation quality stays comparable to the original full precision FLUX. They tested this on standard benchmarks, Genevol and T2I ComBench.
That's kind of amazing.
It really is. And another key thing, it's a post-training method. They didn't have to retrain the whole giant model. They had applied this after it was trained. And get this, they didn't need any image data to calibrate it. It uses self-supervision from the original model. Okay, so wrapping up the summary, 1.58-bit FLUX looks like a really big step towards making these powerful T2I models usable on devices that just don't have tons of memory or compute power. It's about practicality.
Definitely. Okay, so let's dive deeper now.
Let's start with the why. Why is this quantization thing so critical for these big image models right now?
Well, like you said, the models that are really pushing the envelope, think DALL-E 3, SD3, Midjourney's latest, FLUX 1.1, their power comes from their scale. These massive transformer architectures, billions of parameters, that's how they get the nuance, the detail.
But that scale comes at a cost.
Exactly. Directly translates to huge files, yes. But the killer is often the inference memory. When you ask the model to make an image, it needs a ton of RAM or VRAM, and that's probably the single biggest hurdle stopping us from running these things easily on our laptops, or, the dream of having it on your phone.
Yeah. If you want local private AI generation without needing a data center connection, you need smaller, more efficient models. It's essential to shrink them without totally wrecking the quality.
Which leads right into their solution. 1.58-bit FLUX.
So they picked FLUX.1 dev, which they just call FLUX in the paper, basically. State-of-the-art at the time, importantly, open source. Makes it a great testbed for this kind of foundational research.
And the main idea was applying this extreme low-bit quantization, specifically to the vision transformer part, because that's where most of the parameters are, that 11.9 billion number.
Let's unpack extreme low bit a bit more. Normal models use, 16-bit, maybe 32-bit numbers, lots of possible values.
Right, floating point numbers with lots of precision.
But here, they force the weights to be only +1, 0, or Necker's 1, just 3 options. That's the 1.58 bits per weight idea. And they did this for 99.5% of those weights.
It's like simplifying the model's internal language dramatically. Instead of shades of gray, it's black, white, or nothing. They do mention this megas 1, 0 plus 1 idea is similar to what BitNet B1.58 did for language models.
Oh, okay.
But the key here is applying it to image generation, which is a different beast, and doing it post-training. That's the PTQ, post-training quantization.
And that PTQ part is a big deal, right? Because retraining these huge models is incredibly expensive.
Massively expensive. So being able to take the existing, well-trained model and just apply this quantization process afterwards is huge.
Plus, you mentioned no image data needed.
Yeah, that's another clever bit. Their PTQ method calibrates itself using just prompts and signals from the model itself, not the original giant image dataset FLUX was trained on, which is great because often you don't even have access to those datasets.
Okay, so they simplified the numbers. How does that turn into those big efficiency wins we talked about earlier, the 7.7x and 5.1x?
Right, let's break that down. Storage first. Those 1.58-bit weights, the 9-1, 0 plus 1, can be stored very efficiently using just 2-bit signed integers. You just map each value to a 2-bit code. Compared to the original 16-bit numbers, that's a huge compression. Figure 2a shows it nicely, 7.7x smaller checkpoint file. Imagine downloading that.
The 7.7 times smaller, that's already useful, but the inference memory, the 5.1x reduction, that feels even more critical for deployment. How'd they get that?
That's where their custom kernel comes in. Standard GPU math libraries, they're built for floating point numbers. They aren't optimized for doing matrix multiplication where all the weights are just manic 1, 0 or plus 1.
So they had to write their own specialized code.
Exactly. An optimized linear kernel designed from the ground up to handle these ternary weights super efficiently. It minimizes memory movement and crunches these specific numbers fast.
And that custom code is what unlocks the memory savings.
Pretty much. Figure 2b shows the result, that 5.1x reduction across different GPUs. High-end ones like V100, A100, sure, but also importantly on more accessible cards like the L20 and A10. They even note the A10 couldn't run the full precision FLUX out of memory, but the 1.58-bit version worked.
That A10 example really drives it home. It's enabling things that were literally impossible before on that hardware. What about speed, though? Latency, time per image?
Yeah. That's where the results are a bit more nuanced. Table 3 shows this. While storage and memory saw huge drops, the overall inference latency, the actual speed, didn't improve by that same massive factor everywhere.
Okay. But you mentioned some gains, especially on the lower-end cards.
Yes, exactly. On the L20, for example, they saw a decent 13.2% speed up. And for the A10, well, going from out of memory to any speed is effectively an infinite improvement, right? So it definitely unlocks performance on certain types of hardware, even if it's not universally 5x faster yet.
Okay, makes sense. Smaller, much less memory hungry, enables new hardware. But the million-dollar question, did turning 99.5% of the weights into just 3 values destroy the image quality?
The critical question. And they really went after this with standard benchmarks. They use GenEval, that's about 550 prompts, testing composition style, things like that, and T2I Combench, which is tougher, testing specific skills like counting objects correctly or handling complex spatial stuff across 8 categories. Thousands of images generated for evaluation, all at 102E4 by 124.
High resolution 2. And the verdict, tables 1 and 2 in the paper show.
They show performance is comparable. That's the key word they use. The scores for 1.58-bit FLUX are remarkably close to the full precision version on both benchmarks. Even in tricky areas like counting or spatial reasoning, it holds up surprisingly well. Not identical, but very, very close for such extreme compression.
They mentioned something about the custom kernel and quality.
Right, they actually used the minor differences they saw with and without the custom kernel as a sanity check. It helped show their kernel was doing the 1.58-bit math correctly, not introducing its own errors that hurt the final image quality.
Gotcha. And beyond the scores, they included visual examples.
They did. Figures 1, 3, and 4 have side-by-sides. Prompts like a cat made of seawater, dragon made of fire, photo of 3 birds, pentagonal badge, and pyramidal crystal. And honestly, looking at them, the 1.58-bit versions look strikingly similar. Supports the benchmark data pretty well visually.
Okay, just quickly on the nitty-gritty. The calibration process. Right. No image data.
Correct. Image data-free calibration. They used a set of over 7,000 prompts from other benchmark data sets, like Party 1K and the T2I Combench training split, to set up the quantization parameters. No need for the original, massive, often private, FLUX training images. That's a big plus for actually using this method elsewhere.
And it was specifically the linear layers in the main transformer blocks that got quantized.
Yeah, the weights of the linear layers inside the FLUX transformer block and FLUX single transformer block. That's the core of the vision transformer, where that 99.5% of the parameters live.
How does this fit into the bigger picture of AI research? Quantization isn't totally new, right?
No, definitely not. Quantizing models, especially LLMs and even other diffusion models, is a super active area. Lots of different approaches, PTQ like this, QAT, where you train with quantization in mind. But applying this specific, very aggressive 1.58-bit PTQ to a model like FLUX, which is state-of-the-art open source T2I then, and doing it without needing image data, that combination seems to be their key contribution, making it work for this scale and type of model.
Okay, so we've seen the problem, the clever solution, the impressive results. But like any good paper, they also talk about limitations. Where does 1.58-bit FLUX still fall short?
Yeah, they're upfront about it. One main area is that raw inference speed, the latency. While the memory savings are huge and it runs on more hardware, it didn't consistently make image generation dramatically faster across the board.
And the reason for that?
They point to a couple of things. First, they only quantize the weights, not the activations, the values flowing between layers. Quantizing activations too is harder, but often needed for bigger speedups. Second, even their custom kernel could likely be optimized further. They basically say, here's a good start, but there's more speed to be squeezed out with better kernel engineering.
Makes sense. More work needed on the software side for speed. Any quality limitations?
While it's generally comparable, they do note it can sometimes struggle slightly with rendering really fine details, especially if you're generating at very high resolutions. You might lose a tiny bit of fidelity in the most intricate textures compared to the full precision model.
So, okay for the overall picture, but maybe if you're a real pixel peeper focusing on tiny details, you might notice a difference.
Potentially, yeah. That seems to be the trade-off at this extreme level.
Yeah.
And their future work section naturally points towards tackling these things, improving kernels for speed, finding ways to preserve those fine details better. The ultimate aim is clearly getting robust, high-quality T2I onto devices like phones.
This has been a great exploration of 1.58-bit FLUX. Really interesting stuff.
Yeah, to recap, it feels like a significant milestone. Successfully taking a huge state-of-the-art T2I model and crushing its parameters down to 1.58 bits for almost the entire core transformer.
Using that clever post-training image data free method, and then coupling it with a custom kernel to get those really impressive efficiency numbers. 7.7x smaller storage, 5.1x less inference memory. That's practical. That makes it runnable where it wasn't before.
And crucially, doing all that while keeping the image quality comparable to the original, as shown by the benchmarks and visuals.
So for you listening, what's the takeaway? Well, if you're an AI researcher, this paper really highlights the potential of going to these extreme low bit widths for generative models, especially T2I. The data-free PTQ is neat, and it hammers home how vital specialized kernels are.
Absolutely. And if you're an ML engineer thinking about deployment, those efficiency stats, particularly the 5.1x memory reduction, are game changers. It could totally alter the cost and feasibility calculations for deploying powerful image generation. Opens up possibilities for edge devices or just cheaper cloud inference.
And even if you just use these tools or build apps with them, this points to a future where amazing image generation isn't locked behind expensive hardware or cloud subscriptions. It's a big step towards powerful AI being more accessible, maybe running locally, privately on the gear you already own, even potentially your phone someday.
It really does make you wonder, thinking about those limitations they mentioned, but also the potential.
Right. If this much efficiency is possible now without totally breaking the quality, what's next? We still need faster speeds across the board, maybe better handling of ultrafine details.
So how much further can we push quantization and the custom hardware or software needed to support it? Can we get truly pervasive, high-fidelity generative AI running smoothly on everything? What kinds of apps or creative tools become possible when you have state-of-the-art image generation just sitting there ready to go in your pocket?